And the other thing he's doing that's important to our field is that he's mining our records of many years, and he has published and is publishing a lot of interesting things. Tonight he's going to talk about basically a project that in 2000 was selected as outstanding civil engineering project in the United States, and it was the moving of our national treasure, or one of our treasures. So I'd like to introduce Dr. Spertman as our speaker tonight. So welcome, Dr. Spertman.
Well, thank you, David. It's certainly a pleasure to be here. Is that coming through okay on the mic? All right. I was fortunate in 1999 to get a most unusual consulting assignment. I found out that they were going to move the Cape Hatteras Lighthouse, and the consortium that won the competition. There was a competition amongst 6 groups of engineers and contractors that put in design, build, competitive plans, and one of them was chosen. And the one that was chosen was the International Chimney Corp, and their geotechnical engineer was MacTech, or Gibbs Law, as it was known at the time. They had a very comprehensive quality assurance and quality control program, all internally policed. And one of the requirements was that the geotech group, as well as some of the other groups, have an independent peer reviewer. And I was lucky enough to be chosen as the geotech peer reviewer to look over MacTech's shoulder and give them my thoughts. And you'll see I had a few thoughts, and some of them were actually implemented. The title is a bit presumptuous. The Dilatometer moves the Cape Hatteras Lighthouse. Of course, I put single quotes there just to put it in a little bit of context. Physically, of course, the dilatometer didn't move the lighthouse. The lighthouse weighed 4,900 tons. It was 208 feet high and about 55 feet at the base. So, of course, nothing as simple as a dilatometer is going to move anything. However, it played a role, and I'll explain where the lighthouse was, why they moved it, a little bit of a history, and then get into the role of the dilatometer and show you how we used it and what we did with the results. So on to the next slide. The Cape Hatteras Light, there it is. It's actually quite a structure. It's 208 feet high, as I mentioned. It's made with over 1 million brick. It's essentially a hollow brick spiral or conical shape. The foundation is, well, there's brick behind here. It's decorated with Vermont granite. The foundation consists of about 5 feet thickness of Vermont granite blocks, forms a mat, and that sits on top of a wooden mat foundation, a timber foundation. And the reason they did this is because they tried to drive piles, and they couldn't get the piles any deeper than 6 feet. And so they decided that they wouldn't drive piles, and they'd put it on a mat foundation at a depth of about 6 feet. They used local timber. They sent a crews out to cut down pine trees, and they used heart of pine timbers. And 130 years later, they exposed those timbers, and they were still in perfect condition. So that's quite remarkable. They were quite surprised. And of course, the secret was it stayed below water the whole time. The water table's down about 4 or 5 feet. Okay, next, please. Wait a minute, stop. We're going to have a little video, a little dramatic introduction to this dramatic structure.
On a brisk November morning in 1868, men from Baltimore came by ship to this bay on the west side of North Carolina's Outer Banks. Their daunting purpose here, at this isolated, storm-swept beach of Cape Hatteras, was no less than to build the tallest brick lighthouse in the world. These humble men, joined by island laborers, endured storms, shipwrecks, sickness, and the threat of starvation. But 24 months later, the job was done. And on December 17th, 1870, the oil lantern was lit, shining its warning 24 miles out to the sea. It was then that construction foreman Dexter Stetson and his men stood back and proudly gazed at what would someday be known as America's greatest sentinel, the Cape Hatteras Light.
I tried to make it short and sweet, and it actually worked. So that's pretty neat. Okay, next. This is to give you an idea of where the Cape Hatteras Lighthouse is located. We have the map of North Carolina. You know, Washington, D.C. is up here somewhere. We have Virginia, North Carolina. And out here we have the Outer Banks, a series of barrier beach islands. I need to get closer? Okay. I wander around. All right. And here's a road map of this part of North Carolina. There are the Outer Banks. And you can see they're sticking out into the Atlantic Ocean. The lighthouse is located right here. Where it sticks out the furthest in the ocean. And there are shoals that go out at least 50 miles, and it's a graveyard for ships. This was recognized a long time ago, and the first light of any kind was in the early 1700s. And there's been a light of some sort ever since, and they've gotten progressively larger, heavier, taller, and the final culmination was the Cape Hatteras Lighthouse that we're talking about. Next, please. All right, never mind. Yeah, good. I wanted to give a little credits. This is the National Park Service emblem, and the National Park Service is the client. They're the ones that paid to have the lighthouse moved. They wanted to save this historic national monument, even though it no longer ceased to operate after about 1970. It was superseded by more modern technology, but they wanted to maintain it. And it's quite an icon. They get over 500,000 visitors a year to the lighthouse. They have a nice parking lot, a big parking lot, and they have a visitor center. And you can go in and you can go up to the lighthouse now. You can go into the lighthouse. It's really quite a place, but it's very isolated. You're out in the middle of nowhere when you get out into the Atlantic Ocean there. And if there's a hurricane, there's only one way out. Whoops, wait a minute, not quite finished. This is, Dr. Kraps mentioned the award of the year from civil engineering. That's the little statue. That's the award statue. And this is Law's logo. So Law Engineering, I was very much involved with them, of course. And as I'll show you later, Al Tice from Law was my lead contact with Law Engineering, and he's the one that I mostly dealt with. All right, next. And there was a succession of lighthouses, and in 1983 they finally decided to build something substantial, And this is a stone lighthouse, 100 feet high, with what at that time was a fairly modern oil-lit lamp. I think they used whale oil at the time. And it could be seen about 15 miles away on a clear night. But it turns out that 15 miles wasn't enough. They needed to see further than that. And eventually, the hue and cry was such, and also the Atlantic Ocean was advancing on this thing, so they decided they would build a new one. And in 1870, they completed the lighthouse that we're now talking about. And 129 years later, they moved it. Next, please. Just to give you an idea of why they moved it. Because it's a barrier beach island, we have a moving shoreline, and the island is changing shape. This is where the shoreline was, with the ocean on this side and the sand on this side. That's where the ocean was in 1852. And in 1960, this is where the shoreline was. So the island moved to the west. This is westward. It also moved to the southward. And here is the lighthouse. Originally, it was 1,600 feet from the high tide line. At the time they moved it, it was only 150 feet, and it had been that far, or that close, I should say, for, at least 30 or 40 years. They were fighting what was essentially a losing battle to try to keep the shoreline away from the lighthouse so it wouldn't be undermined. It, of course, is sitting on sand. These are sand dunes that it's sitting on. And the sand goes to a depth of at least 75 feet, which is the maximum depth investigated. Next. All right, here are the remains of that 1803 lighthouse. At various, it was demolished after the 1870 lighthouse was finished. And during its history, even though it's only 600 feet away, it was partially underwater. Not currently underwater, but the island has shifted around, so it's a good thing they moved it. Otherwise, they would have lost it without having to demolish it. Next. Some views from the top of the lighthouse, just to give you an idea what the country looks like. This is looking north, and there's the Atlantic Ocean. There's this narrow barrier beach island. It widens in this part of the island. You can see how close the water is at this point. The next view will show you even better how close it is. Next. That's looking straight down from the top of the lighthouse. And it's only about 150 feet away, pretty close. The Corps of Engineers made monumental, and that's a pun, made monumental efforts to keep the water away from the lighthouse. They did all kinds of things. You can see the remains of a sheet pile groin that they built. They used beach replenishment. They used riprap. They used sandbags. They even used artificial seaweed to try to get the sand to accrete on its own. And basically, all of these worked for a short time, but in the long run, they didn't work. So they finally decided they had to bite the bullet and move the lighthouse. Next period. This is looking south, and the movement path is right across here to the far end of this parking lot, a distance of 2,900 feet, more than a half a mile. And they ended up back to that 1,600 feet distance from the shoreline that they had in 1870. So they're back to the 1,600 feet, and they hope that it lasts another 130 years. This time the foundation is a lot better, as you'll see. When you go to the Visitor Center, you can pick up this as one of the many brochures, and they have quite an interesting exhibit, including videos on the movement of the moving Hatteras, relocating Cape Hatteras Light Station to safety. And this is a dramatic view showing you how close the ocean is, and also indicates there's not much elevation difference there. I forgot the elevation it's sitting on, but it's probably less than +10. So it was in danger. Here's that sheet pile groin telling you about. Here's some of the riprap you can see. They tried, but the sea eventually wins out. Next. Here's what the move corridor looked like before they started clearing it. So this is what was the vegetation on the dunes, just scrub trees and bushes and some grasses. Anyway, this all had to be cleared, and the swath that was cleared was, well, about 100 feet wide, mostly 80 feet, I guess. They cleared an 80-foot swath through this, 2,900 feet long. Next. This is Al Tice, a little thank you, Al. I made one visit to the site, spent a few days there, and I took this picture at the time. And Al kindly let me look through some of his slides. He's made presentations as well, and I picked out a few of his slides. So there's our acknowledgement to law. Next. I like to annotate my slides. I just take a pen and write on them. But here's the lighthouse, of course. I put down 3,000 feet. It's pretty close to 3,000 feet. It's a 3,000-foot move, actually 2,900. And this is the equipment in an excavation, which has been dewatered, and they're preparing the new foundation for the lighthouse. Instead of being timber and Vermont marble, it's going to be reinforced concrete and brick. So they have a 70-foot square reinforced concrete mat, 5 feet thick. And when I say reinforced, I mean really heavily reinforced. And on top of that, they're going to move the lighthouse. Then they're going to build a brick foundation to replace the marble. Did I say marble? Granite. Replace the granite. And then they're going to lower the lighthouse onto the brick foundation, which in turn is resting on this reinforced concrete mat. Next. Well, to move the lighthouse, the first thing they have to do is, of course, dig an excavation, dewater it, but they were careful not to dewater below the level of the top of the timbers. And then they had to remove the granite, and the next photograph will show some of the granite being removed. They put a steel mat on top of the timber as they were excavating. Then they put these steel, well, what you call them? I forgot the name of them, but they're basically little groups of 4 columns held together by steel cross bracing, and the supports, of course, they're intended for supports, but a jack on each leg, so that eventually they can use these supports for jacking the structure. Over 100 jacks, and the jacking pattern was typically in groups of about 35 on a triangular pattern, so that they could tilt the structure in any direction they wanted to by working 30 jacks at a time. 35. The plinths are here being protected by some wrapping to keep the dust from removing the granite off of them, to keep them clean. And there's a perimeter beam around here which is acting as the lateral bracing to keep the foundation from spreading during the move. Next. Here they are in the process of removing the granite, and they had a wire diamond saw running on a band, and it's not quite clear, I suppose. You can't see it, but there's a cut right here, and the wire saw is actually working on this cut. It cut these blocks at a rate about 1 foot per hour. Pretty slow cutting, but they were very patient. They would remove some of the granite, put in these support towers, the steel support towers, and then they'd remove some more, etc., back and forth, till eventually they had all of it removed, and they were resting the lighthouse on these support towers. Next. Give you an idea of the pile of granite. This is the granite that they undermined out of the foundation, and the weight is roughly 1,000 tons of granite removed. So it's quite a rock sawing job, sawing, S-A-W-I-N-G. Well, once it was gone, they didn't use it again. The new foundation is on brick instead of this granite. Next. Here we have the moved corridor. They have essentially transferred the weight of the lighthouse onto these support towers. They've made this clearing. They've leveled it. It's 2,900 feet from here to here. They're ready to start the moving process. One of the buildings around the lighthouse has already been moved. It was over here before. They moved it over here, down here, now they're turning the corner up here. And this is the eventual location of the lighthouse. There were a number of smaller structures that were also moved because they wanted the pattern of the lighthouse and the various support structures to look exactly like it did before the move. Next. A little schematic of the load transfer system, which is very complicated. There are beams, crisscrossing beams on rollers with jacks. They eventually transferred the support towers, the weight on the support towers, onto wood timber cribbing. And they jacked up the structure. First they put some lifting beams under it. They jacked up the structure, built this cribbing up, and then lowered it back down off the towers, the steel towers, onto the cribbing. And so the building was, the lighthouse was supported on the cribbing, and of course the support was along this railing. These are, well, it's a support mat, and these are steel rails, and the tower is going to roll on the rails. These are rollers. They're called Hillman rollers. They're very massive, essentially big roller bearings, and very low friction, of course. That was the whole idea. And there are jacks here, and these are the push jacks. So the push jacks are pushing it, the lift jacks are lifting it, and the lift jacks provide the control for keeping the tower vertical during the move. That was the idea. Next. Here's the same thing in kind of a sketch format, a little bit artist's rendering. And here are the cribs. Well, first of all, here's the wood cribbing at the bottom. Here are the steel mats under the cribs. The cribs are holding these beams, which are the rail beams. And over here, those rail beams are supported on a steel mat. These are the jacks that are holding up the tower. I call it the tower, the lighthouse. And they're the same beams. These are massive beams. These are made-up beams. They're not just simple beams. They're made up. The rollers are inside the beams. The jacks that are holding up the lighthouse are also inside these beams. And the whole thing is designed to roll, including the jacks. The jacks had a 6-inch throw. They could move 6 inches. So whatever differential settlements we had, and whatever settlements and differential settlements we had, they had to stay within the adjustment capability of those jacks with a 6-inch throw. Maximum of 6-inch movement. Now these jacks had a big movement. They could move 5 feet. The push jacks had a 5-foot throw, and could move it. It was quite a job to get all of this lined up, and it took them quite a few months. And it took roughly 6 months to get to this stage. And then they started pushing it down the track. This, by the way, the cover plates on these steel beams are hardened steel. So these rollers rolled on welded plates of hardened steel. Not the ordinary steel of an I-beam. Next. All right, now a little bit about the soil conditions. Here's a cross-section through the move. We've got these rail beams, and they'll call them the transport rails. There's a steel mat underneath that. There's a 30-centimeter or 1-foot layer of compacted stone to help spread the load. And we're sitting on the natural dune sand, and it was rolled at the surface with a fairly light roller just to prepare the surface. And underneath that, we have the dune sand, and we have the water table down at around 4 feet. And in this sand, we have loose zones. I'll just call them loose zones. They are layers of sand that have a significant amount of organic material, and they have significantly more compressibility. The estimated compressibility of the upper 10 feet was, well, put it this way, about 80% of the settlement would take place in the upper 10 feet. And in areas where we had loose zones, half of that settlement would be due to the loose zones, even though the maximum thickness of loose zone that we detected was only 1.5 feet. Next. Well, I thought you'd be interested in comparing the standard penetration test values with the DMT value profiles. And what I have here is, in red, I have the blow count. Can you see the red? 10, 20, 30, 40, 0. And down in the bottom, we have a scale for the dilatometer modulus values in bars. And this is the depth in feet. Now, remember I told you that we really only worried about the upper 10 feet. The lower 10 feet was much denser. Everything below 10 feet was much denser. And so that was not a primary concern. There were a large number of borings made, and I'll get into that just a little bit now. The Corps of Engineers made a group of about 25, roughly, borings in 1983, down to a maximum depth of 54 feet. Then when Law became involved, Law made an additional 10 standard penetration test borings at about 300-foot centers down the move, and their maximum depth was 75 feet. Then at my suggestion, they did 21 DMT soundings down to maximum depth of approximately 5 meters, because that's as far as they could penetrate. But that was far enough. And it gave some indication of these loose zones. So again, at my request, they did a lot more dilatometer tests searching for these loose zones to see what their extent was and whether or not they would present a problem for the move. And they did an additional 63 soundings for a total of 84 DMT soundings. But the additional ones only went down to a maximum depth of about 8 or 9 feet. So that's the extent of the SPT and DMT investigation. Next, please. We attempted a correlation between the dilatometer M and the standard penetration test N, and all the comparisons available were only at 2 locations. We only had 2 locations where the two were parallel to one another. We can compare them, assuming there was no difference in a horizontal distance of 5 to 10 feet. And here's the correlation. There's a point here and a point here as well. And the correlation was M equals 60N. At least that line is an approximate correlation. Now, I didn't care about this correlation, but law did. And so we did it. They also did it. But there are a couple points over here which are not in the correlation, and those are probably from the thin organic layers, where the N value is too high because standard penetration test encompasses a distance of 18 inches. And these are rather thin layers. Next. This is a field load test which was done at my suggestion. I call this a conical test load. Some of you may be familiar with my conical test load. And I talked them into doing a conical test load. Now, it's easy to talk people into doing this because it only takes about a day to do this test. And there certainly was plenty of sand. And the instrumentation is really simple. You just put a plate on the ground, you attach a pipe to it so that you can get a survey rod down to the plate, and you pile dirt around in a conical shape, and you measure the settlement. And you end up with a field measurement of the compressibility at that particular location. The maximum height was 15 feet. The diameter was 60 feet. And the total weight of that test load was 750 tons. So pretty significant. And I'll show you how significant. Next. The conical test load was done in 3 steps. Went from 5 feet high to 10 feet high to 15 feet high. And at each stage, they stopped filling and they made a settlement measurement. They waited half an hour or an hour till the movement stabilized, and then they put on the next increment of height. We have, here's the depth, the 5-foot level, the 10-foot level, and the 15-foot level. And we had 10 feet of relatively loose sand, and then below that was denser sand. But here's the thing that's important for something like this. We calculated that this test load produced 66% at a depth of 5 feet of the anticipated full load of the lighthouse when it rolled over this spot. And at the 10-foot depth, that was 52%, and at the 15-foot depth, it was 46%. So this test, although rather simple and quick, tested the foundation to a very significant percentage of the final anticipated loading. And that's one of the advantages of this, I call it the conical test load. It, in a quick, easy to construct fashion, can often provide a very significant loading in the way of a test loading for a site. Next. Well, we used that to help calibrate our method of calculation for settlements. Now, of course, as I mentioned before, settlements were very important. If the settlements and the differential settlements went outside the range of the adjustment of the jacks, there was serious trouble. Kind of dramatic weather overhead, too. Here are these columns are the conical test load height, the calculation for settlement in inches by law, my calculations, which are done independently, although we both use the same method, and these are the measured values. And I used the very simple 1986 procedure, the same one really that Marchetti recommends, and that is you just take the load increase, the stress increase at some level, divide it by the modulus at that level, multiply it by the thickness of the sublayer, and add all the various settlement increments together to get the total settlement. It couldn't be simpler. Of course, you may have a problem of what do you choose for calculating the stress increase, and I chose the simplest, Husson-esque elasticity. So here are the predictions for settlement. I'm sorry, here are the predictions. Here's measured. 0.14 compared to 0.19, 0.34 compared to 0.31, 0.60 compared to 0.44. We considered this excellent and conservative agreement. So I also checked it just myself against the strain factor method, 1970 strain factor method, and the settlement was much greater, and so we decided that was no good. But of course, the strain factor method, which was developed for rigid footings, was never intended to be used under a pile of dirt in a conical shape. So we didn't really expect it would be any better, and it certainly wasn't. So we ended up using this method, very simple method, elastic theory, and that's what we based the movement predictions on. Next. All right, we're getting ready to move now. And here is the structure. It's on its support beams. They're building the rails, and they're going to start the roll, and they're going to roll it in this direction. Next. Oh, wait a minute. Yeah, press it again, because another picture will come up. This shows the jacks that were used in the push. There were 5 of them, and each one, as far as I know, could push 60 tons, so 300 tons of push. One interesting thing about this is that the jacks were clamped hydraulically against the beams. Of course, they had to successively move them. They would push the lighthouse 5 feet, and then they would move the jacks, push it another 5 feet, so forth. So they had a simple system for moving these. They just slid them along and clamped them hydraulically for the reaction. And here you can see the high-strength steel plate, hardened steel plate, on which the rollers ran on top of the track beams. Next. Well, the lighthouse is almost there. This is what the move looked like, looking down on it. Here is the foundation, the reinforced concrete foundation, the mat that is ready for the lighthouse. Here are the advanced mat of beams. As the lighthouse moved this way, they took the various mats and beams off of this end and moved it around to the front. And so they had kind of a moving track. Pretty close to finished now. Next. I wanted to mention one more thing before we kind of compare predicted with measured settlements during the move. And that is, there is something different about a rolling move. It's not the same as a static load. So I introduced a correction, at least I talked law into listening to my introduction for a correction, to account for the fact that it was rolling. If this is the print of the support beams that hold the lighthouse, and this is the direction of the track, if it's moving in that direction, first it's subject just to the edge load, then it's subject to the center load, and then back to the edge load. The total settlement, when that happens, is going to be greater than if it just stood there and you measured or predicted the settlement in the center. Because it's really shear that controls settlement, and the strain factor method that I mentioned is really based on that idea. It's the shear strain distribution that's important, not just it's the shear stress distribution that's important, not just the vertical stress. And in particular, the ratio of shear to vertical. Well, I calculated that using elastic theory for a point at various points along the move, and then drew an envelope. You might call it a shear envelope. And I compared that with what the shear distribution looked like without the rolling. And if you think about it, the settlement is going to be proportional to this area. So this area represents the settlement onto the center point if it's a static load, and this is the additional area that represents the additional settlement for a rolling load. And the ratio of those two is a ratio of 3, which is this area, plus 1, which is that area, divided by 3, and it's 1.33. So I suggested that they multiply the static calculations by a 1.33 factor, and law eventually used a 1.25 factor as a compromise. So there's some justification for that because some of the settlement will be below 10 feet, and the factor is not as great for the settlement below 10 feet. Next. Here's what the settlement pattern looked like during the move. This is just a typical set of data. Of course, law monitored very carefully the movement of the foundation, which in this case is the bottom steel mat that's resting on the 1-foot gravel layer, which is resting on the sand. Here's the direction of the move, and you can see it's a dish-shaped. The largest settlements are in the center, and they vary from, this is the 25 contour, I guess. I can't read it, 25 or 26. The maximum settlement here is 28 millimeters. We're now in millimeters. So it's a little bit more than an inch. It goes all the way down to 6 millimeters. Here, that's the minimum reading, 6, at least the contour of the minimum. So we went from 28 to 6 in a dish-shaped. And the effect of the roll, you can see it, because it's rolling in this direction. So where would you expect the maximum settlements to be after the roll is completed? You'd expect this to oval towards the back. And it does. So there was some effect of the rolling on this settlement pattern. Next. Okay, here is the bottom line we worked so hard to take a look at. This is a plot of the move settlements, the track beam identification and spacing. So this is the center, these are the edges, here's the legend. This is what was measured for the typical zone and for a zone with some of those loose layers. So the typical zone was about 11 millimeters at the edge, and approximately 27 millimeters in the center and back to 11 or 12 at the edge. And in the loose zone, we had 25 millimeters here, going down to about 52, and up here about 19. So those were the actual typical and maximum settlements during the move. And here's what we predicted. We predicted these points as typical and these points as maximum. When I said we, it's actually Law that made these predictions, and this is a figure from a paper that Law presented. Well, first of all, we were conservative. The actual measurements are only about roughly 2/3 of those predicted. That's good. We were in the right direction. Secondly, they were very well within the limits of the jacks to control the movement, to compensate for the settlements. And in reality, the move was done remarkably successfully. And there was some pressure to do it in a hurry because they wanted to complete it before the hurricane season started in August of '99. It was actually finished in July, the mid-July. It took 22 days to make the move. So if you figure it out, that's an average of about 130 feet a day. If you figure that out, what do we have? About 5 feet an hour. So every hour they repositioned the jacks and pushed it another 5 feet. Very slowly, of course. People in the tower were monitoring vibration instruments, all kinds of instruments. The report was that they could not even tell that the lighthouse was moving. They had to stick their heads out the window and look down to see whether the thing was moving or not. And they were sitting on top, up where the light is. The contractor had no issues and no delays resulted from any kind of movement problems. I told you the movement took 22 days. They completed it ahead of schedule because they allowed 30 days for the movement. As far as tilt goes, the maximum tilt that they decided the structure could withstand without beginning to inflict its damage on itself was 1.3 degrees. 1.3. The actual movement was it never reached 1/10 of a degree. It was always less than 1/10 of a degree. So this lighthouse moved essentially perfectly vertical. And so it's a huge success story. Needless to say, they threw one big party when this thing was finally moved. It went flawlessly. I asked Al Tice, and he said he was aware of no problems during the move. Everything went according to plan. And I'm not aware of any problems. And that brings me to one sort of statement I want to make. And let me see if I can find it. Professor John Mikowski said that a case history like this is really not valuable unless you learn something. Preferably you have some kind of a minor failure, not minor, and then you dramatically learn from it. Well, I can't add a failure, but I think law engineering did learn something from it. They produced a paper for geostrata, and it is titled Geotechnical Planning, Design, and Construction for the Cape Hatteras Light Station Relocation. Written by Al Tice and Randy Knott. And at the very end, sort of in a conclusion section, they start with lessons learned. And they say, the analysis performed for this project demonstrated that the settlement behavior of sands under large area loads can be conservatively modeled using constrained modulus values from the dilatometer test and elastic layer analyses. So let's have the next slide. Maybe moving was an exaggeration, but it certainly helped. Thank you. What's the tradition? I'm willing to answer questions, if we have any questions. Can we back it up one? Are you talking about this slide? Okay. Yes. The 1.33, well, law changed it to 1.25, but that factor was included. That factor was included. And if we hadn't included it, it would have been just about right. Yes?
How does the final mat perform?
The mat? Oh, yes, that's a good question. They measured the settlement of the mat when the lighthouse was finally on top of it, and I think they had a maximum settlement of 13 millimeters. Well within what they expected, yes.
So it's within their predicted?
Oh, yes, yes. It's only half an inch. Yeah. Well, any other question? Well, thanks again.